Hi everyone, I'm Rachel Livermore in Melbourne, Australia, and I'm here with Jeffrey Silverman in San Francisco, California.
And today we have a guest who's an old friend of mine from grad school at Berkeley. He's now a postdoc at the University of Texas at Austin. Dr. Aaron Lee is with us. Hey, Aaron.
Hey, yeah, Facebook told me today, as of recording, we have been Facebook friends for 9 years today.
Oh, isn't that sweet? That's great.
Aw.
Yes, we knew each other early in grad school.
And you're in Austin, where Rachel and I were just about a year or two ago, and you're drinking one of our favorite drinks from there. What do you have with you today?
Indeed. Supporting local business by drinking Austin East cider.
Oh, one of the best ciders out
I'm,
there. Very good.
I am really envious. As someone from the original cider country, that is the one American cider of which I thoroughly approve.
Yeah, I between undergrad and grad school, I spent a year in England and then just fell in love with cider. And I'm so glad to now be in a place where cider is a thing.
So aside from cider, Aaron works on trying to figure out how stars form from big clouds of gas and using large computers to figure out how those clouds turn into stars. So why don't you start us off, Aaron, just kind of describe what are the basics of how stars form? How do we get a baby star born?
Gravity. Next question.
All right.
No, I often joke that if you want to know how anything really works in astronomy, gravity is typically the answer. And that is definitely the case with star formation, where you have large clouds, and can be tens of parsecs in size, so very large clouds of tenuous gas that collapse under their own gravitational tug and pull. And that gas, some of it gets to a dense spot where then that gas becomes hot enough, and you might form one or multiple stars.
So, what can we learn about the way our own sun might have formed from looking at other stars forming?
One thing we can learn is we can ask: is the sun typical? Is the sun common or not when we look at other stars in the Milky Way and in other galaxies around the universe? And we find that the sun is an average kind of star.
But stars tend to be born in families, right? Is our sun typical in that respect?
That is true. Stars do not form in isolation. So going back to these large clouds of gas, now these can have enough gas to form hundreds to thousands of stars. There's plenty of gas in these clouds, and as they collapse, a fraction of that gas gets turned into stars, but they never form just a single star. These clouds are forming many, many stars. Either hundreds to possibly thousands. But then something happens that typically causes these stars to run away from one another or depart from one another. So, for example, you are probably familiar, viewers, with the Orion Nebula. It's one of the coolest things I like to point out in the sky, mainly because as a theoretical astronomer, it's one of the few things I know where it is in the sky. And if you find the Orion constellation, you find the three stars that represent the belt, and you look right under the belt, where you might imagine his sword would be if he had a sword sheathed or something. You can see a fuzzy patch of light. And that fuzzy patch of light is not a star, but that's actually part of the Orion Nebula. That is in that small part of the sky, that's actually, a region of space that's tens of light years in size, that's forming hundreds of stars as we speak. Now, that is an example of one of these natal birthing grounds. In that cloud is four very big stars, which are called the trapezium stars. And in the next million or so years or so, those stars are going to start to die. And these very massive stars die as grand supernova explosions. And we are fairly confident that when that happens, it is going to completely obliterate the Orion Nebula. So those individual big stars are going to just destroy everything around it, and all the stars that have already formed will just get flung out into the universe. So it's quite possible our sun might have formed in a cloud just like that, where something happened, be it a violent supernova within the cloud, or maybe something a little more quiescent that caused the sun to drift away from all its siblings that it formed with, likely 5 or so billion years ago.
So you're a theoretical astronomer.
I have never once used a telescope for research.
That's impressive. So how do you use supercomputers to learn about star formation?
something that theoretical astrophysics wants to do, particularly when you're doing simulations, is I want to create, to the best approximation as possible, nature on a computer. This shows you an example of how I take a box of gas. So initially I just have a box of gas. You can imagine I'm just taking a giant ladle and just stirring it up. And I'm just mixing it all up. There's magnetic fields, and so fluids are going left and right, and the magnetic fields are bending and turning, and I get an image that looks like what you're seeing on the screen. And what is useful is that these can be compared to the sorts of regions that we see in space, and these sorts of images that you see are representative. So what I'm creating in my simulation is representative of nature.
So how did you get into this line of work? Were you always a coder?
So yeah, computer science has always been something I was always very interested in. And I think it was just a serendipitous thing where an advisor I worked with at Northwestern, which is where I did my undergrad, I was looking for a summer project to do. I wanted to really get into astrophysics, and he happened to be a theoretical astronomer. And it just so happened to be that was his interest as well. And so it just ended up working out that I was able to discover a project that kind of combined all my interests, which broadly is kind of how I got into astronomy as well, because I thought astrophysics combined what I liked about physics and what I liked about mathematics, and then in addition, what I liked about coding.
I feel like we've heard that kind of answer from a number of guests. They had, a good experience with a good advisor who had a kind of interesting project, and the subject matter was interesting enough, and then that sort of put them on a path for their research career.
Yes, I completely agree. Yeah, a good advisor or a mentor, I'll say,
Sure.
can do so much. They can also do a lot of damage. But we'll save that for another episode. But yeah, I was really thankful to. I am thankful to Fred Razio, who's he does a lot now with gravitational black holes and a lot of the gravitational wave stuff he's involved with at Northwestern now. Really cool stuff. But yeah, the fact he gave me a chance to work on some N-body stuff. So this was more the motions of planets around the star. That's kind of my first project as an undergrad. And the rest is history.
So you're an expert on three-body problems then?
Yes. Lots of three. Yeah, it was definitely, my first paper was about three-body problems.
There you go.
Well, it seems like that worked out really well for you, and I hope you're enjoying Austin. I know we both miss Austin a lot. So thanks very much for talking to us today, and cheers.
Cheers.